Hi everyone, and thank you who have signed up on today's webinar on research and development in the transformation of UK consumer price statistics, organized by the Best Practice and Impact team. I want to give a quick background information about the Best Practice and Impact team and the idea behind the sharing webinars. BPI is a service for all those who work with government statistics. We work with statisticians and other professions across government to improve government statistics through advice, consultancy, training, guidance, and champion networks. The aim of the sharing webinars is to share any identified best practice across government departments via the sharing webinars, and so we can learn from each other. Today's agenda, we're going to have 5 presentations from our colleagues in Office for National Statistics. Each presentation is going to last about 20 minutes, and then we'll have 5 minutes for questions after each presentation. We're going to receive questions via Slido, so please use the Slido if you want to raise any question with the code consumer price statistics. Please do not use the Google Meet chat for any question, and make sure your microphone is on mute so we can avoid any interruptions during the same webinar. The first presentation for today is from Helen Sands, who's going to give an introduction to inflation and alternative data sources project. I'm going to hand over to Helen.
Thank you. Are you able to see my screen?
Yeah.
I think you're still sharing yours, Nikki.
Yes.
Okay, so morning everyone, and thanks for joining today. So as Nikki said, I'm Helen Sands. I lead the research team looking at including new data sources and methods into our consumer price statistics. But with me today, I've got several of my colleagues from across the ONS who are involved in the process, from acquiring the data in the first place to building the new systems to handle the larger data sets, and also researching new methods to use with the new data. So that's the outline for the webinar this morning. Hopefully you're all here because you already have some kind of an interest in inflation, but for anyone that's not too familiar with its traditional measurement, I'm going to quickly cover that, along with an overview of the new data sources we intend to use and our timetable for the development. And I'm going to hand over to my colleague Kim Young, who is going to discuss data acquisition and building relationships with suppliers. Matthew Price is then going to talk a little bit about how we are going about building a new analytical pipeline to process the new prices data alongside our traditional data sources. And then for the last hour, we'll move on to some of our main research topics from the last year. So Liam Greenough will talk about how we've been using supervised machine learning models to classify our web scrape clothing data. And last but not least, Alex Rose will talk about some of the new index number methods that are available for use for price statistics and how we try to choose an appropriate method. So moving on, I'm just going to quickly cover what inflation is. It will be a very quick introduction to inflation, so if you do have any questions or want to know more about how we measure it, do feel free to drop me an email after the session. So consumer price inflation statistics generally measure price changes for a sample of goods and services across a sample of locations and retailers in the UK. The sample of goods and services is often referred to as a shopping basket or simply a basket of these goods and services. Many things are linked to inflation, so anything from mobile phone contracts to rail fares, pensions, wages, even government debt. So that means that the rate of inflation has an impact on every individual and every household in the UK. So it's therefore really, really important that we measure it as well as we possibly can. So in January of each year, we select a sample of over 700 goods and services to track over the year. That choice of items is based on consumer spending and trends and is refreshed every year to add and remove items. So to give an example of that, in 2020, we added in reusable bottles and gin in a tin. So each item in the basket is given a weight that reflects its economic importance. So for example, if more people spend money on petrol than baked beans, then price changes for petrol would naturally have a greater impact on the price index than baked beans would. So in terms of data collection, approximately 180,000 price quotes are currently collected each month for thousands of products. Most of these prices are currently collected manually from physical stores, at least in the non-COVID world, as well as manually sourcing prices from retailer websites and phoning businesses. As a side note, that's largely how prices were collected over the lockdown period. So we're here today to talk about alternative data sources, but now I'll just quickly discuss what those really are. So this next slide shows our traditional data sources and how they compare to two new types of data that we have available. So the first data source we now have available is known as scanner data, which is point of sale transaction data that comes directly from the retailers themselves. So these data are aggregated across a week or a day so that no individual purchases can be identified. The scanner data is essentially gold practice, gold standard for price statistics. It includes all the transactions from the retailers, generally includes metadata, but its biggest benefits are that we know how many of each product have been sold, and we can generally access the historic data too. So this allows us to use weights at the very lowest level of the calculations and look at the impact of using scanner data over a number of years historically. So the other new data source that we have available is known as web scrape data. So that's where an automated tool scrapes retailers' websites for prices and returns a data set of basically prices and metadata in a data frame that is ready to calculate price indices from. Web scrape data comes with similar advantages as scanner data, and that it has better coverage of products and a higher frequency of collection than traditional data sources, but it doesn't have that extra level of detail that scanner data has with regards to how many of each product have been sold. So they're the main differences. The plan is not to use scanner and web scrape data wholly in place of traditional data sources, but to use all of these data sources together to provide a detailed overview of price change within the economy. So we will continue to collect prices manually from independent stores and stores that don't have an online presence. Also a number of services we will need to collect the prices manually for, but where possible we will look to obtain the scanner data. And where we've not been able to yet get scanner data, but we do have permission to scrape a retailer's website, we will look to use web scraping to improve coverage and frequency of collection. But note that all of our web scraping is carried out in line with the ONS web scraping policy that you can find on our website. So this is the proposed future structure of consumer price statistics using all these data sources. So I'm now quickly going to cover our broader plans for the methods and data transformation in terms of our timelines before handing over to my colleagues to talk in more detail about some of the other areas of the project and the challenges that we face. So our key milestone to note on this slide is early 2023, when we first plan to implement new data sources into consumer price statistics. In the lead up to this, we have 3 phases. So this year we've been focusing on research and development, so looking into the methods and systems that we're going to need in place to be able to process these data. Next year we transition into our application phase, where we can start applying our methods to categories of interest while further developing our systems. And then the following year we plan to publish historical impact analysis from using the new data sources, as well as parallel run of the impact during 2022. So we plan to continue publishing research articles, impact analysis, and holding user events throughout this timeline. So we welcome feedback at any point throughout that process. This slide just shows our current priority items. So these have been decided through discussions with our key stakeholders. For now, we've decided to focus on groceries, clothing, tech goods, used cars, airfares, package holidays, chart collected items like CDs and DVDs, and computer games, and rail fares. Although we do plan to roll out to other categories in the following years. These prioritised categories are all areas where we think we can probably substantially increase the quality of our estimates through the use of scanner and web scrape data. So this next slide is just a really quick overview of our pipeline for processing consumer price statistics that Matt's going to talk about a bit later. It's a modular build and it's still in development, but it allows us for a lot of flexibility, so we can test and visualize different configurations of methods easily. It's built in line with ONS strategic systems and software, so I think Matt will talk about that during his presentation shortly. And finally, just to mention that there's still a large research program underway before we will be able to use the data sources. So firstly, we need new methods of classifying the big data that Liam will cover later, and better index number methods, which Alex will cover later. As well as this, we are also looking at whether we can approximate product level expenditures for web scrape data to bring them in line with the kind of standard that we're getting from the scanner data. And with regards to the scanner data themselves, we're researching how we can effectively capture and adjust when products are relaunched. So sometimes products are relaunched with slightly different sizes or packaging, so how we can capture and appropriately adjust for that, how we account for returns and discounts in these data, and also how we can handle changes in any of the units of measurement. To deal with high levels of churn within some of the markets, we're also looking at whether we can follow groups of very similar products over time rather than tracking the price of each unique product. That should help us to deal with turnover in areas where there's high fashionability or rapid technology change. And big data comes with very different handling methods. So these scanner and web scrape data are huge compared to what we're used to. So as such, we're researching new methods to effectively detect and validate outliers, as well as whether we need to impute for missing values, and if so, what the best way to do that is. And lastly, we need to ensure that we are using appropriate data sources and weighting schemes to aggregate together these new data sources with our traditional data sources, which is something that we're working through at the moment. So just to quickly wrap up that brief introduction, new data sources have many advantages over our traditional manual collections, but there's still a lot of research and development that's needed before we can make it happen. So we plan to first introduce these improvements in 2023. So that's the end of my presentation. I don't know if there are any questions yet or whether we can move straight on to the next presentation. Thank you.
Thanks, Helen. There's nothing on Slido at the moment, but I do have one question, if that's okay. I don't know much about this area, so this might sound really weird, but looking at those priority areas and particularly the used car type thing, in the data, does it reflect the price that things are advertised at, or if there's like deals made in the particular business where someone says, oh, I'll give it to you for this price, is that captured, or how does it work there?
So for our traditional data and for the web scrape data, we generally just get the list price, so it's advertised at. The benefit of the scanner data is that we do get that transaction price, so we get the kind of overall expenditure that's being paid per product and the number of quantity of the product sold. So from that we can work out the average price that that product is sold for, which is kind of why the scanner data is that gold standard for us, really, because we can see the actual price paid, but awesome. List price.
Oh, that's great, thank you. Yeah, nothing on slide at the moment, so I think we're okay to move on to the next presentation.
Okay, great. I'll hand over to you then, Kimio.
Hello, thank you very much for that. So I will share my screen as well. There you go. Can you see this one now?
Yeah.
Yeah, okay, very good. So hello everyone. My name is Gumnyang Min. So I'm head of commercial data acquisition and operations in ONS. So I'm going to tell you a little bit more about the very early stage of the engagement, such as when Helena was talking about the pipelines and the very beginning about the data sources, and that's where my team gets involved. So I'm going to tell you a bit more about the data acquisition or what the division does, and also how we build up the relationship with the suppliers. So it is going to be around 15 minutes, and then we have some questions at the end. So I would be roughly introduce a bit more about what does data acquisition and operations do, and how does data acquisition fit into the ONS statistics production in terms of the pipelines and then the entire process itself, and also tell you a bit more about how we bring the data in, and also the data sources that we contact and we also collect, and also other things that we consider when we talk to our suppliers, and any other challenges. So if there is no other burning questions, then I will crack on. So as Helen already mentioned something about it, so when we are producing the statistics, mainly there are two different sources being used, such as we collect the data, such as local price collections, as well as the census, any other surveys that we do, as well as the other admin data we're getting from the external organizations. So in order to identify any of the research gaps or the data gaps, then we engage a lot with external organizations, and then that's mainly our job. So data acquisition and operations, DAO, or some people know our division as data as a service before, is actually the first contact point with all the data suppliers, also the engagement with other business areas. So we technically create the link between the admin data collection and the use in ONS data, so ONS statistics. So then what we actually do, so we are the single voice in ONS. So what we normally do is that we engage with our business areas to identify any of the data requirement across ONS. So it's not only about the one business area or the other. We work with the PPA area, public policy area, as well as economic statistics area. And then what we do is that we collect all the data requirements and so on. And then we identify whether the other data sources would be required. And if the data is required, then what kind of data sources are available, and then which data suppliers might have the data relevant. So, but you can imagine that there are a number of the suppliers outside, and then maybe one data set can answer multiple research questions. And but if individual business area or contacts back to the suppliers, the burden on the suppliers is quite huge. So that's the main reason why we exist. So what we do is that based on the all ONS across the requirements, we collect all the requirements together and reach out to the suppliers, and then we try to get the data once that can be used many times in ONS. So we're technically providing linkage between two. So then data acquisition itself is not just about the acquiring data. So it's not just about the data supplier. We contact them and ask them, can you give us data, and then sort it. It never ever happens that way. So we are technically engaged in all the process from the identifying the data requirements, and then checking the feasibility and availability of the data and any other data sources in the market, and also delivering the data itself throughout the negotiating the data sharing terms and conditions. So we work with the external government departments, commercial bodies, devolved administrations, or NGOs as well. So then in order for us to work very closely with the business areas and then deliver the data that's been required, so what we normally do is that we also provide advice, because such as scanner data can be used not only for the price index, but also for for example, health maybe. Health kind of providing some suggestions for the consumptions related to the health issues as well, maybe migrations or the spending, business activities, and so on. Then what we do is that we have to understand the data requirements um, very deeply, because otherwise we can't go back to the supplier and then being true representatives of ONS. in that sense. So, and also we can't bring all the data business areas in the one room. Therefore, we technically becomes the one key point, collect all the data queries, and then deliver that one to the suppliers and negotiate any of the data sharing terms and conditions, any requirements, any quality issues, and so on. And once we get any data, then we again reach out to our internal users, not only the ones that we are working with, but across the ONS. So, such as we received I don't know, we recently negotiated one of the data sharing terms and conditions with scanner data or used cars or the VOA data and so on. Then we share that information across the ONS throughout the gateways so that everybody is aware of the what data sources have been brought in. Therefore, they can actually see if they can be useful or not. Yeah. So we kind of provide the contact points between ONS as well as external and across governments as well. So just the quick numbers. So of course we have more than 150 data sharing agreements. So sometimes we have agreements with one supplier, or sometimes we have multiple agreements to cover the multiple data sets with the one organization as well. So, and that means that we also deal with all the data sharing agreements and MOUs. We provide any of the service on that side. And of course, we collected 210 plus unique data sets and data ingestion, such as any data sets that come into the ONS that comes to our data ingest team. So who is going to ingest all the admin data into our data access platform, which has more than 800 users. And then the number is increasing over and over because at least for my team, at least we are dealing with 30 plus suppliers per month. So you can imagine how the number will grow significantly. Then how we actually bring the data in. So we normally follow the data acquisition and ingestion 7-stage models. So you can see there 1, 2, 3, 4, 5, 6, 7 there. So it normally starts with the requirements and scoping phase. So this is where we work with business areas to really identify what is needed. So what kind of questions they try to answer, what statistics has to be provided, what data gaps there is, and what might be the alternative data sources they need. And after all this scale and scoping exercise, then once we identify that that's the ONS priority, then we reach out to the suppliers. So this is early engagement, such as testing water types. So we contact the suppliers, see if they actually have the data, or if they are willing to engage with us, or if they are even sharing data with us. Yeah. And then once the supplier is willing to engage with us and they are able to share the data with us, then we go into the negotiation phase. So that's when the data sharing agreement is technically created at the end of this phase. So this is not only about the legal requirements, and then we provide all the information about the security, governance, any cost implication, and delivery timetable, data specs, anything that you can imagine that has to be agreed with the supplier is done that stage. And then once the negotiation is nearly done, therefore we know that when the data is going to come in, how the data is going to come in, and then that's when the delivery management starts. Or sometimes the 3 and 4 happens at the same time. Once we know the data is coming in, and data actually comes in, then we do the ingestion. So we receive the data, we ingest that one to our secure data environment, whether that could be that or somewhere else. And then we also check the data and then do the basic quality checks. And then the data can be processed and standardized by our data engineering team in data architecture. And then we also provide a user for that data set in that sense altogether. And once data is available, cleaned, all tidy, ready to use, then that's when the business area can access and then they can use it for their statistics. So by only the end of the 6, then that's when the production of the statistics and the business area actually starts. So we are talking a lot earlier than any of those pipelines that Helen mentioned. And then of course we also manage any of the existing data sets we have done, so such as BAU functions. That's what we do as well. So that's kind of 7 stages we all follow. You can also see that data acquisition gets involved quite hugely across all the process. Then I will talk a little bit more about what's happening with where we actually get the data from. So you can imagine we get the data from almost everywhere. So the ones that the larger kind of our key government partners such as HMRC, DWP, Home Office, VOA, Minister of Defense, Justice, DEFRA, BASE, whatever you name it, more or less we have a relationship with them. And as well as education sector, health, local councils, entire local councils across NGOs, and devolved administration. We work very, very closely with them. And also the businesses, such as all the scanner data, retailers, we get involved, use the car, utilities, and utilities data we get involved, and then financial transaction, anything you can name it or mention it, more or less we get involved. So if you have any questions around the commercial sector, that's where we're coming in as well. Then how normally the supply engagement happens? So we first have to have some of the internal discussions, such as is it the office priority, or does it actually support our transformation plan? Also, is the data actually available? Is it something that's actually out there? Or maybe it's not. Or the business area, do we have the budget for it? Or how about the data ethics or security or governance? Can we actually get the somebody's name and address and the telephone numbers for our statistics? Probably not. Then what is our legal basis we can use? So we do a lot of this ONS consideration before even reaching out to the supplier. So once we have some agreement, we're saying, okay, this is what we are going to do, and that's allowed from our data ethics and security and governance perspective, then we start to do our background research on the suppliers and markets, alternative data sources, and then we start to talk to suppliers. But then even then, we still have to consider when we are talking to the supplier whether they actually have the data or they might have data, but they might not be able to share with us because of their legal restriction or sometimes operational restriction. Also, how sensitive the data might be, because especially with the commercial suppliers, they care a lot about the confidentiality. So sometimes they say, we can give you data, but you shouldn't tell anybody that we are giving you the data. If you have the multiple suppliers like this, how are you going to manage the relationship with them? And how about the data protection? Because they do care quite a lot about that side. And we have to provide kind of a large chunk of the security assurances and so on. So that's what we do too. And how about the resource or cost? Because we normally get the data for the public good, but sometimes suppliers might actually ask for some tangible benefit, such as can you pay us, or can you actually give some data for us? Sometimes we do get that request as well. So it's kind of a very tricky balance because we of course wanted to be seen as the partner of our suppliers, but at the same time we have our own restriction and obligation. So it's a lot about kind of keeping the balance between two. So then what kind of challenges do we actually talk about? So it's all about the could be communications, such as when there's a COVID-19 pandemic started, all of a sudden some suppliers went very, very quiet because their priority changed, or they don't have resources anymore, or sometimes they realize that they are not going to get any money or anything back from us. They might become quiet, or sometimes internally we just waiting for. We are not quite clear about what we are actually asking, or there is miscommunication. Therefore, we ask a thing, and later we have to actually change our requirements and so on. So we have to be really, really, really working close with everybody involved. Otherwise, it could go quite disaster, and it's not very good for the ONS reputation either. So we have to kind of keep the very kind of a fine balance there, and also priorities. So as I said, sometimes it is the priorities changing from the supply aspect, but also sometimes it changes from internally. Yeah. So all of a sudden, census becomes a priority. Then all of a sudden, this is COVID-19 is the priority. Then where does it go? Because we have only limited resources. So then how we best allocate our time and resources to get the best output. So that's kind of a challenging part as well. And also we have so many different teams involved. So it is that we are the central team, but we work very closely with the legal team, procurement team, of course, business areas, and sometimes external affairs and the security, DST. So it's all about the kind of finding the right balance and then negotiating the best ones for us as well as them. So we try to provide a mutual benefit, and but then it doesn't mean that we can do whatever we like or we can we can promise anything. So we need to kind of keep our negotiation in a very kind of tight, controlled manner, and also the unpredictability in itself, such as environmental one, COVID-19 pandemic. What can we do about it? Or sometimes we all of a sudden receive the huge data set at once. Therefore, the pipeline gets blocked sometimes, some of the technical issues. Or sometimes the supplier says that we can give you data, but only via a method, which we have never done it, or our firewall doesn't allow it. Then we also need to kind of identify technical solutions as well. So there are multiple challenges all that, and then you probably know a little bit more about the legal aspects as well. So you probably heard a lot about this one, the Statistics and Registration Service Act, SRSA 2007. So that's our main piece of the legislation. So if you see any of the agreements we have drafted, you will see this name over and over coming in, because that's what sets out what we can do and what we can't do. And the Digital Economy Acts, and then other ones are GDPR, and then Data Protection Acts, and so on. So technically, that's all the kind of challenges. I mean, I have to say it's not easy process, but it's actually kind of a key aspects that we can do to deliver to everyone. Nikki, is there something that you wanted to say? You okay? No, because I heard that, so I just thought that maybe I'm doing something wrong. You wanted to tell me about it. So that's all the things I can tell you a bit more. And of course, there are other aspects that I could share. Depends on the questions and then the requirements you have. Web scrapping policy, we own them as well. So if you have any request for the web scrapping, please do contact us as well. So that's it. So unless you have any questions, please.
Thank you, Gyeom-young. There is a question from Lucia in Slido. She asks, do you assess the quality of the data during the negotiation or scoping phase?
So this is so we mainly do all the data specs. So then we do ask them all about, like, you know, how does it look like, what do you provide, and so on. And then we actually ask them to send us the sample data or test data. But then, do we actually see the main data? We don't, because sometimes even before the agreements, they are not allowed to share any data with us. So that during the negotiation stage or scoping phase, we can't actually assess the quality of the actual data. So what we can do is that throughout the constant engagement with the suppliers, we ask them as many information as we can and ask them to provide us the data specs, and then dummy data or test data, sample data. We also hold sometimes the data spec workshop. So kind of throughout the data share, the screen sharing and so on, they actually show us that what it looks like. Then we agree on the indicators or any specific specs and so on. But then, as you can imagine, once we actually receive the data, when you actually check it, it might not meet it, so that it constant loops in that way. Does it make sense? Yeah.
Yeah, amazing. Thank you.
Yeah. Anything else?
No further questions, I think.
Okay, well, we are here if you have any questions. Thank you very much. I will stop sharing and I'll pass to the next one.
Brill, I think that's me. And someone pipes up and says a voice. Share my screen would help. Dun, dun, dun. You are presenting. Hopefully you can see that.
Yeah.
I was going to say I'll take silence as a good thing. Okay, so yeah, good morning. I'm Matthew. So I'm the technical lead for the Alternative Data Sources project. So what that means is I'm leading the team of developers building the pipeline that we've been alluding to so far. So we're a team made up of data scientists, data engineers, software engineers, but because of how we work on the project, we all kind of get involved in all those aspects. So we're quite a varied bunch. I appreciate how we build an analytical pipeline isn't maybe the most gripping title for lots of you, so I'm going to hopefully stay away from using loads of jargon and this is code, and instead I'm going to look to give you the broad strokes of how we're approaching the task in front of us, the motivation behind how and why we're making the choices we've made, principles of best practices we're employing in the team, and then I'm more than happy to answer more in-depth questions at the end, or we can take it offline. You can email me and bounce ideas around or whatever. But in this talk, I'm going to focus on these 4 areas really. So data sources, which have been covered quite nicely in the previous 2, so hopefully we can skim over that a little bit. I'll talk a little bit, well, only touch on really the system we're building this pipeline to work on. Then move on to look at the design considerations for the code from our perspective, the user perspective, etc. And then finally moving on to this idea of reproducible analytical pipelines and how this ties in with those previous 3 points and how we're using it on the project. So data sources, so obviously before building the system, it's important to consider what the data sources are we're going to be running through our code. So as we've had mentioned before, we've got currently the conventional data sources, so these locally collected data, and then we're going to add into the mix these alternative sources, so scanner and web scrape. And because of, as has been touched on, the fundamental step change really in the size and complexity of the data sources we're going to be using, so the scanner and the web scrape, we need to rethink how we are processing the data to calculate these CPI statistics. So in particular for these new data sources, then we have the fields I mentioned. For scanner, we've got the price, we've got this quantity, which is really quite revolutionary for us to have now. We've also got the item names, and we've also potentially have access to retailer classification hierarchy, and then this data is coming in weekly versus how the local collection data might come in. Similarly for the web scrape, then we've got the price, because it's web scrape, you potentially have all the product description, so, a very verbose description potentially. When that price was scraped, and we could be doing that daily, or more frequently, less frequently, and also the retailer that comes from. But then because the data is so big and we have all these fields within the data and they're coming from lots of different sources now, rather than, we have a contract set up to do the local collection, so there's a standard way that's done. Retailer A scanner compared to retailer J scanner data set could be very different. So we need to really consider the data we're using and how that's being fed into our pipeline. Which leads me onto this idea of the consistency and the quality of data. So, like I mentioned, one set of scanner data could be very different to another set of scanner data. So, retailer A might call the number of items sold quantity. Retailer B might call it number sold. How they handle returns in their data could be very different. Perhaps it's negative prices. Perhaps there's a whole different column which says all of this information is for a returned product. And also, it might not just be one big table of data, it could be several tables of data. This one might just contain the prices, this one contain all the detailed product information. So we need to work to make sure that these are joined together appropriately, so we have some kind of consistent data from retailer to retailer. Similarly then, for the web scrape data as an example, these unique identifiers for each product that we web scrape, we want to make sure that that's consistent across different retailers, because you want to be able to compare like for like from retailer to retailer. So before even building our pipeline, we want to make sure the data is consistent. And so we're quite lucky, there's quite a big team of us, so able to work with the suppliers to identify those common column names, for example, quantity is quantity, number sold is quantity, returns are handled like this. And then working with data engineering, we can create databases for all these different data sets that are consistent and the same. So no matter if I'm looking at retailer A, B, C, D, I know that it's going to have these columns. The type of data in this column is always going to be the same. So it just means then, from the pipeline perspective, it doesn't matter what data I'm feeding into it. I know I'm going to get the same processes occurring to the data. And then there's this other idea then in the second point there. So for data, we may have the size of the product. So a bag of rice could be 400 grams. Equally, you could have I remember being in Tesco during lockdown when they were running out of stuff. There was, those 5 kilogram bags of flour. But you can't compare a 5 kilogram bag of flour to a 400 gram bag of flour, because using just the unit, because 5 and 400 are very different. So working with data engineering as well to get this idea of a standardized size in the data. So instead of 5 kilograms, it's 5,000 grams. And then we can compare that very like for like to 400 grams of flour. So they're all really important aspects in the data that is really important to get sorted before you actually start processing it. And something to really come to appreciate during COVID now as well, working on faster indicator publications to make sure that the data is really consistent before you start processing it in anger. Otherwise, you might get bitten later on by something surprising you're not expecting. So now, just quickly to talk about the system we're building this on. I won't go too far into this. So we're using something called DAP, the Data Access Platform. This is a computing system set up in the ONS for housing all the sensitive data, hence the name Data Access Platform. And how this works is we have a Cloudera data science workbench on there, so somewhere to run the code, and that is connected to this HDFS, so Hadoop distributed file system, which is where this data is stored and then where processing happens. And we have 3 flavors of DAP. So we have dev test, which is where, as you might guess, we develop the code and test the code. It's the most up-to-date version. It gets the updates first, but then it's not connected to the live data. So we have to create synthetic versions of our input data to run on there. Then we have this pre-production system, which is connected to a small cluster and live data, which is where we can test the code before we push it to production, which is where the end user will be running the system in a couple of years' time to produce CPI. And this will be a massive system where we can process all this data at once. It's very stable, but because of that, it gets the updates last, which is why then you can see there's this tiered way of developing the code, testing the code, and then making sure it works before pushing it through to the actual live system. And hopefully by the end of this talk, you'll be able to really appreciate the benefits of having these systems. You might be thinking, well, why do you need 3 computers to do one task? Just use one computer to do it all. So hopefully later on, when we talk about the reproducible pipelines, that'll become clearer a little bit. So in terms of the design of the system, we're using Python, common, well-supported computing language, together with PySpark, which is a Python API which is written to allow us to use something called Spark. And Spark is basically a computational engine that works with massive data. So obviously we're talking about our scanner data, billions of rows. Using something that works with massive data sounds ideal. And it does this by doing the processing in parallel. So instead of having to process row 1 to a billion one by one sequentially, potentially you do process the first 10 million rows here, second 10 million on parallel, in parallel, and so on, so on. So you're reducing the actual runtime of the system. So it's a much more computationally efficient way to process the data. And then our core pipeline is built such that it needs some minor configuring by the user, and then you send it off and it runs end to end through a series of modules, which Helen touched on in her slides at the start. And these modules can include steps such as pre-processing, classification, averaging, product grouping, imputation potentially. And this is really useful then, because by building in a modular fashion, it means that we're able to work with methodology on individual parts of the code to ensure that they're, the best methods we hope to be able to employ. And also then, if something potentially could be spun out into a larger system, so classification as an example, within the pipeline we have a classification step where we do some keyword matching to classify products. So for example, if we were looking at laptops, if the product description contains the word bag, it's probably not a laptop, it's probably a laptop bag, in which case it's probably got a very different price, and we don't want to count that as a laptop because it would really skew our price indices, for example. So we do that. However, when you move to more complicated data sets like clothing, which is what I think Liam's going to be talking about a bit later on, so I won't delve too far into that, you might want to do something more complex using machine learning. So then building this modular fashion means we can spin that out into its own entire pipeline and then hook it back into our core pipeline at the same step. So building in this fashion really gives us a lot of flexibility in how the entire process works then. So I touched on there working with methodology. So because really we don't just want to make up our own ideas, we want to really make sure, because it's going to be a official statistic, we're using robust methods, and also because a lot of these ideas, imputation isn't a unique prices idea. We want to develop systems that can be shared across other parts of ONS through this idea called the statistical methods library. So it would be a library of standard statistical methods in the name, which anyone could just pull and use. And on our project, for example, we found there's over 20 of these methods that should be shared wider across the ONS. So by working with methodology and developing our system in a robust manner means that we're well placed to feed into that loop as well then. And then just quickly on user interactivity. So the end user is obviously not expected to be a code developer, and I'm talking about using Python and PySpark and doing all this and that. But we want to develop it so it's very straightforward to be run. So we have a very simple configuration file, which doesn't, all you need is a text editor, and the user can just update. And in that, they can tweak the parameters that go into different modules, because obviously at the moment we are a research project, so we don't have a set in stone imputation method or averaging method or index method even. They want to be able to vary and see how they affect the outputs of the pipeline. So through this configuration file, the end user can tweak these, and then also outputs are saved from the pipeline for each module. So you could go in and look at, say, well, I ran this entire pipeline, but I'm not sure what the outliers were. You can go in and check at that particular point in the pipeline and see what outliers were identified, and then you could maybe tweak your outlier parameters to expand or contract or whatever. The world's your oyster, basically. And then we also have visualization. So we've got a dashboard which will visualize all the outputs as well, because personally I think a figure is a lot quicker to disentangle than a very large table and really pull out insights. So RAP, what is it? I've kind of mentioned it a little bit there. So RAP stands for Reproducible Analytical Pipeline, and it embodies this idea that at any point in the future, we should be able to look back at the work and be able to reproduce everything that we did today in 5 years' time if we wanted to. And that's obviously something that's very difficult to do with these kind of manual, semi-manual processes where you tweak stuff as it goes along, or even ad hoc codes which people write and get passed on through several people as these things do, and then it ends up being a production system, and you're like, how's that happened? But it's happened now, okay. And then you're kind of stuck with something that you don't really know how it works, and maybe you couldn't go back and reproduce a result from 2 years ago because it's a bit of a black box. So by employing this idea of wrap, we can look to avoid those pitfalls by having code that is not reproducible, or is poorly documented and therefore difficult to maintain, or as a black box, i.e., you just push your data into it and assume it's going to come out right. Wrap really prevents that from happening. And so the cornerstones, in my opinion at least, are recorded history of development, which you can achieve through version control of your code and also your data, potentially. Peer reviewing the code, so by the developers, to make sure that best practices are being employed, so you're not developing, like I said, we're a big team, but you could, in theory, develop in silos and not really know what everyone else is doing. But by having peer review of the code, you have a good idea of what everyone's doing, share knowledge, make sure everyone's really producing the best code possible. Or also by the end users end to make sure that they agree that the method you've implemented is actually the method they described to you, and you're not just doing something completely different. Then this next one is really important. So thoroughly and appropriately tested. So really making sure that each method does produce what it should be producing. It handles the edge cases. If my data set's got a load of missing values, should it be producing an output or should it throw up an error, those kind of things. So all the tests to make sure that's happening. And then this idea of it being well documented. And that's, so then obviously in 5 years' time, everyone who's developed the code could have moved on to somewhere else, but someone else might want to pick up the code and, well, probably for this system, be able to pick up the code and know what's going on. And by having good documentation, they should be able to pick it up and understand, okay, this does that, that does this. So just to go into that a little bit more now, so the version control, so we are using software called Git, which basically lets you keep a recorded history of all your code through development. Each change is recorded and you can roll back the code at any time. And then we're using this, it's called a Git flow branching strategy, so that development is containerized such that each feature being added into the code is done separately, so you don't affect the current system that's running. So in theory, if we had the system running in production, we can continue to develop whilst not affecting the current outputs. And then we're doing this in an agile manner, so we're doing sprints and all the rest of it. And then we have a Jira board where we go and have a ticket for a task. A task is something to be developed in the code, and we work in that way to actually do the version controlling of the code then. Peer review. So like I mentioned, multiple developers review the code. So say I work on a feature, say, I don't know, some new price index method. I write the code, I submit it to the group. The group then will go through the code and check to make sure that I've written good code and not just written something that's pretty rubbish. Make sure I've documented it well, make sure I've got the tests in place to really cover all the scenarios. And then also by doing that, it means that if I then dropped off the face of the earth, someone else would understand the code I've written because we've gone through that review process, and hopefully could step in and continue to keep it up to date if something was wrong. And then testing. So really important, because like I said, if you want to be producing official statistics, you want to make sure the system is working and it's not going to do anything weird without you noticing. And you have to do that by really testing the individual components of the code through both negative and positive testing. So what I mean by that is testing it with scenarios that should happen, scenarios that shouldn't happen. So, like I mentioned, maybe all my data set is full of missing values. That should probably isn't going to happen, but we should make sure that we cover that edge case and really make sure that happens for every piece of the code. So then we work with both the research team, the methodology, and BAUs, the business, like the end users, to make sure that all these tests are covering all the aspects. And then documentation, like I said, really important. So we have 2 levels of documentation that we look to employ. So there's low-level documentation of the individual functions within the code. So these can be automatically generated from the code using other Python packages, and they can be really very insightful if you're a coder. So like in this example here, it's an index method. You know, you can actually put in the full mathematical equation for that index method that helps you relate what the code's doing. You would say my function expects these parameters, which are of this data type. It returns this parameter of this data type, and that can be really useful to trace through and make sure you understand what's going on. Say if you want to expand or link in functions from somewhere else. Then we also have high-level documentation, which is very useful for the end users. So, you know, it's not the nitty-gritty codey bits, but it gives you the idea of, I start my code here, I run, this happens, I put in this configuration potentially, this happens, that happens. It gives me this output, which can feed into this visualization, for example. And these 2 together then really give a really comprehensive overview of the documentation of the code, which, as I mentioned, then means going forwards in time, people move on, everyone still knows what's going on. And then finally, there's this idea of packaging, which we do for this project using something called Jenkins, which automates the testing and the documentation generation so that we don't push code into the production system if it isn't thoroughly tested and passes all those tests, and all the documentation for the code that the end user would be using would then be automatically updated when we release new versions of the code. And so this is all an automated process. So as long as you develop the code in this kind of wrap manner, all of this just works naturally then out of the box, which is really great for us then as developers, because you don't have to think about it twice. You just do it when you write the code, and then it's done. So yeah, so really in summary, building a big pipeline is hard, and there's lots to consider, but then good communication between everyone really makes it a lot easier. And then building with this idea of reproducible analytical pipelines in mind is really very key. But it's really just making the whole process a lot easier for us, and other people, I think, in ONS and wider in government are really starting to appreciate that as we build these big pipelines to produce statistics, having this idea of wrap in mind is, well, it's crucial really to be able to have faith in your system. So yeah, so that's really all I want to say. Like I said, I've not gone into the jargon there too much, hopefully, but if there are any in-depth questions, I'm happy to answer those as well.
Thanks, Matthew. That's really interesting to hear about those innovations. I'll give the Slido another minute, but I wanted to ask about, so you talked about your plans to publish an official statistic and working with methodology to help with that, but have you published an experimental statistic already, or will that be an experimental statistic first?
So Helen's probably a better place than me to answer this, but they are using the pipeline currently to produce research outputs and research papers that are being published. Just to highlight, I guess, really the development that's gone on so far. Is that fair, Helen?
Yeah, do you want me to chime in?
Yeah.
So yeah, as Matt said, we're kind of using the pipeline at the moment for our research outputs. We're not planning to introduce them into official statistics until 2023, so we will have a parallel run year in 2022 where we'll publish the experimental statistics alongside. Also worth noting that we're using the pipeline in dev test at the moment to publish the faster indicators release.
I meant to say this. Yeah, so by developing in a wrap manner, it means we've been able to quickly pivot all the code to produce weekly indices from some other web scrape data for faster indicators publication. Richard's on UNF every week.
Brilliant, thanks very much. There's no other questions for now, so I think I'll pass on to Liam.
Okay, thanks, Matt. Let me just share my presentation. Okay, so my name's Liam Grinoff. I'm going to be presenting about the use of supervised machine learning to classify alternative data sources, clothing data. I'll start by asking the question, why do we want to use supervised machine learning? And that comes down to the kind of nature of the data that we're collecting. So like it's shown kind of by this graph. So on the x-axis, we've got the month. On the y-axis, we've got the matched sample size, and this reflects the number of products of clothing that we are scraping each month. So a match sample size would be of the products that were scraped in January 2019, how many of those products still exist by, let's say, March 2019. And you can see with clothing, like in particular, the kind of matched sample sizes dwindles very rapidly. Clothing is known as a market that has high product churn, and the kind of problem that this poses us with kind of with the classification task is that even if we were to expend a lot of effort in manually classifying the 800,000-ish products that we collected in January 2019, by the time you get to February 2019, a lot of those products have disappeared and you're going to have to manually classify a whole load more again. You'll have to keep doing this throughout the year. So this averages out to around 150,000 products that you'd have to manually classify every month, and I estimated you'd have to hire 12 people full time just to keep on top of all of that, and that assumes that they don't they keep a constant pace on kind of manually classifying, and they don't get bored 30 hours into their week of classifying clothing data and their kind of rate drops. So like we'd kind of need a bit of a more automated method, a bit less resource intensive, to kind of classify all this data that we are collecting. So this introduces supervised machine learning. I'm going to take a moment to describe how supervised machine learning works as a method, because I know a lot of people aren't quite familiar with it. So with supervised machine learning, we start with a full data set, and we're going to take a sample of the data set, which is represented by these 9 products. With this sample, we're then going to label the data set. So the kind of sample will already contain like some kind of variables that you use as your predictor variables, but now you assign a label, which is the kind of the variable you are actually going to predict in your algorithm. So now you've got like a labeled data set consisting in this example of 9 products. You're going to split the data set into a training data set and a test data set. The algorithm is going to be fitted to the training set, and then we'll see how the kind of algorithm performs on the test data set. I'm going to use an example of what's known as a decision tree. So a decision tree involves making binary splits at each level. So on this training set, you feed the algorithm the training set, and it determines, well, a good way of splitting the data set to begin with is to question, does it have sleeves? If not, then you predict jeans. If yes, then you go into a second decision gate, and then you'll ask, is it blue? If yes, predict a shirt. If no, predict a t-shirt. Now, the kind of does it have sleeves is maybe a good kind of question to ask to split this data, but the question, is it blue, that doesn't work too well. It's only kind of work because the training set consists of shirts that are only blue. It won't generalize well to beyond the training data set when you get other, like for example, t-shirts that are blue. So what we call this is overfitting. It works well on the data you've trained it on, but it's not going to generalize well beyond the data. And this can be shown by how it performs on the test data set. You apply the same rules you've trained your algorithm on to the test data set, and you see that it erroneously identifies a t-shirt as a shirt because the t-shirt is blue. So the kind of approach is you just collect more data for your training set, and hopefully you can learn rules that are just a bit better at predicting your classes. So that's kind of the very basic supervised machine learning approach. I'll now kind of talk a bit about like how we've been using supervised machine learning. So a very first task you need to do is decide which classes are you going to target with your data. We've got a challenge here because there's a bit of a trade-off between how easy something is to classify and how homogeneous the classes you're aiming for are. So, for example, if you were to classify to things as high level as sportswear, then that might be quite easy to classify because you might only need to determine that the clothing exists in the sportswear section of the website or contains some very basic sportswear terminology. But the trouble is that then you've got this kind of class that contains anything from like a kind of £5 base layer bottoms up to a £300 skiing jacket. It's not very homogeneous. It contains many different things, and that's not desirable when you're producing indices. So on the other end, you can go kind of more targeted, like kind of much lower level classes, but then the kind of decision rules that you need to learn are a lot more complex. And so there's a trade-off here, and we are trying to classify to different levels and to see what works. Our goal is to try and produce kind of classes that are as low level as possible while still obtaining a high degree of homogeneity, and performance is still high enough to produce unbiased indices. Like I said before, we need to do some labeling to give ourselves some targets to classify. We are labeling 9,000 products a month using a Python application that we've developed in-house. The labeling is done by the prices division as a collective task across the division. And to date, we've collected well over 50,000 labels by now, and I'll show some of the results in a moment. But there is a challenge with clothing labeling in particular, and that's subjectivity. So for example, this is a genuine product. We had a product which is called a fleece zip-through jacket. Now, is that product a fleece, a jacket, or maybe it's even a fleece-lined waterproof jacket? And in reality, it's maybe in between a fleece and a jacket. Maybe it's kind of some kind of combination of the two. So there might be some subjectivity in how that gets labelled. So we wanted to kind of measure that subjectivity. We wanted to know, have we already approached a point in kind of our classification performance where the subjectivity of labellers is leading to us being unable to obtain any high performance. And what we got was, what we did was we had 12 labellers label exactly the same 313 products. We deemed the consensus amongst those 12 labellers as the correct label, and we calculated how consistent labellers are with that consensus. And you can see in the dot plot on the right, like how where kind of each labeler landed in terms of their consistency with the consensus. So there's this cluster around 0.9, 0.89-ish, which kind of gives us a benchmark for how well we can hope to perform with our classification algorithms. I'm going to talk a bit about the kind of performance of what we are obtaining, but I just want to introduce what, like how we measure performance. So there are three kind of measures of performance. I'm going to focus on the F1, but the F1 is a harmonic mean of precision and recall. So understanding precision and recall leads you to understand F1. So a precision score of 0.8 for women's dresses would mean that 80% of the machine's guesses are actually women's dresses. That is 20% are false positives from other different classes. A 0.8 for recall would mean that 80% of all women's dresses are captured. That means that 20% of the women's dresses are false negatives landing in other classes. And as I said before, F1 gives you like a kind of compromise measure between the two different measures, which is the harmonic mean of precision and recall. So I'm going to focus on F1 as a kind of score of our performance. What we've got here is if you were to train your algorithm on a number of months given by the x-axis, and you were to calculate the macro F1, and now the macro F1 is to take the F1 score of all your individual classes and take an unweighted average across all of them. So if you were to take the kind of unweighted average of the F1 scores when tested on 2 months, then these are the kind of performance you get. So so after 1 month, you've labelled 9,000 cases. You're testing on 18,000 cases. That's 2 months of data, and you get a macro F1 score of just shy of 0.6. When you train on 2 months and test on 2 months, you get something close to 0.7, 0.75-ish. 3 months, you're getting like slightly closer to 0.8, and then when you're training on 4 months, you get just shy of 0.8. So you can see that the kind of performance rapidly increased to begin with, but it's kind of starting to slow down. And I'll kind of talk about a means by which we can perhaps accelerate that training process again later. But this is the kind of performance we're at after training on 4 months and testing on 2 months. And we still think we can do a lot of things to kind of improve our performance, however. I've now got an animation of all the different classes and how they perform based on training on 1 month, testing on 2, training on 2, then testing on 2, etc. So like this animation shows this is training on 1 month, then on 2 months, 3 months, and 4 months. And there's something interesting to know when you look at it at the class level, look at like how the F1 scores at the class level change. So for example, I'll highlight this example here. After 3 months, it's only moved slightly, and then at the 4th month, it's jumped quite rapidly. So it's like it shows that kind of these things don't just gradually increase. Sometimes, like there's a bit of back and forth, and it's kind of graduates in the right direction. So what I guess I'd say out of this is that it's like the kind of performance we're getting in each of our classes hasn't settled down yet. There's still quite a bit of jumping back and forth, so we believe that we can get performance gains about through labeling even more data. I'll now focus on 4 very specific classes. So that's women's dresses, women's jeans, women's sports bottoms, and women's suit jackets. This is training on 4 months, testing on 2 months again, but we're doing it over 5 different classification algorithms now. We've got XGBoost, random forest, support vector machine, logistic regression, and decision tree. There are 3 things to note with this graph. Firstly, decision trees always perform worse, like they a very basic classification algorithm. The 4 other kind of algorithms perform much better. Secondly, the 4 other algorithms do perform reasonably close for each of the classes. And thirdly, women's dresses and women's jeans are kind of high performing classes, whereas women's sports bottoms and women's suit jackets are fairly low performing classes. So we're now going to look at indices based on these kind of classification results. Before I go into the indices, I'd just point out these are experimental. They don't truly reflect market behavior. What we're focusing on here is the closeness of the indices. So when classification performance is high, and you've got a kind of classification performance of an F1 of around 0.9, you can see the indices for dresses and jeans are very tight. Like the kind of 4 main algorithms, the kind of indices like hug each other. Decision tree does slightly do its own thing. Like for dresses, it diverges in July. For jeans, it does co-move reasonably well with the other classifiers, but you can see that is kind of a bit of the odd one out. But what I'd say in general is that when you've got a kind of F1 of 0.9, the kind of choice of classification algorithm doesn't matter too much because they produce very similar things. However, when classification performance is low, you can see that the indices start to spread out. So in the case of women's sports bottoms, they spread out somewhat, but then co-move reasonably well. There is some kind of resilience to classification error there. But with women's suit jacket, they kind of they are completely divergent all over the place. And this is probably because of the low sample sizes of women's suit jackets in the data set, that just a few misclassifications can lead to indices that become very divergent. We still have a lot of work to do, however, with the classification. we are exploring the use of active learning, for example. So we believe that labeling more data will result in higher performance still. However, we have some classes where we've got very good classification performance already. If you were to continue to label in those classes, it'd be kind of very inefficient, I'd say. So we're looking at introducing active learning, which is where you get the kind of algorithm to essentially learn from its mistakes. It's the kind of the products that it's least confident about predicting. You base your sample more around that, so you can accelerate the learning in the areas that the classifier struggles the most with. Second thing we need to do more of is parameter tuning or hyperparameter tuning, which is in a kind of machine learning system. There are a lot of different things you can tweak, and they might affect performance. And so we need to look at like how different combinations of those parameters might lead to optimization of the model to produce higher and better results. Third thing we want to focus on is applying this kind of system to other areas such as groceries and tech goods. Helen introduced a lot of the areas that we're exploring, so we need to look at classification for each of those areas before we go into production. Key messages from this presentation. Firstly, the volume of data means we need an automated method of classification, and supervised machine learning methods are showing promising results for resolving this problem. Generally, the more data we get leads to better models, but there is a ceiling effect largely driven by the inconsistency in how labelers label the data. The choice of algorithm does have a relatively small impact on the indices for high-performing items. But then we still need to do a lot of work to kind of improve our automated classification, particularly for some of the kind of lower performing classes. Does anyone have any questions?
Thanks, Liam. That was really interesting. I'll give it another, there's nothing on Slido at the moment, but if you do have any questions, you feel free to put them there, or you can shout out in Google Meets as well. Cool, thank you. If there's no questions, we'll pass on to the last presentation, which is Alex.
Good morning. Give me 1 second. I'm just going to start presenting. Right, there we go. That should be sharing for everyone. So I'm Alex Rose. I'm a methodologist as part of the Economics Hub, specifically around consumer prices, and I'm going to talk you through the research projects we've done looking into the framework for including new index number methods. So this was the pipeline that Matt and Helen talked about earlier, and it's just to highlight that the index calculations part of it is towards the tail, the last few steps. So why are we trying to change our method? Why do we need to change our method? So the answer is because the data that we're using is going to be changing. So traditionally, we would send collectors into shops to collect a handful of items. This is an example that we've got for bread. We might send them in to get 3 specific items that represent all of the possible loaves of bread that we could purchase in a retailer. One of the problems with this is that it's got limited collection dates. We can only send our collectors in every now and again. And the other problem is that we don't get any expenditure information with it. If we were to then compare this with the web scrape data, you can see already we've gone from 3 products to 147 products if we were to scrape all of the bread products that a specific retailer had. So we're getting more of a census of the basket than rather a representative basket. We can also do this daily, hourly, however more frequently we would like, so we can get an increased collection and produce an average over a month rather than just one specific date. We also get a lot more detailed characteristics rather than what you'd collect in store, which is useful for the classification that Liam was just talking about for one, amongst product grouping and other stages of the analysis as well. But we still don't get any expenditure information when we web scrape. We're not able to scrape a website and say how many of each product has been sold. Then lastly, we have the increased scanner data. We're still getting a full census of data, same as the web scraped. But here we're also getting that quantity sold column. We're able to calculate how many of each specific product is sold. So us moving to use alternative data sources for our consumer prices means that we're going to get that increased product coverage of the market. If we've got scanner data, we're able to weight the prices at the product level. And it also means that we can automate the process fully. So we don't have to send someone into the shop to collect the prices, then upload those prices and then do the analysis that way. It can all be done in one swift pipeline that Matt talked about earlier. But this change to alternative data sources means that the traditional index methods that we use currently for our current collection approach will perform poorly, or they'll break down due to the dynamic nature of the new data sources. And it will also mean that the additional information that we can collect from these new sources is not fully utilized. So how did we go about choosing a new method? So the framework itself is broken into 3 stages that you can see on the left side here, the 3 columns. So the first stage was to shortlist to produce a top 10 list of methods based against scoring on our theoretical framework. So this framework included the theoretical properties, which was looking at the axioms that have been set out for index number methods, and then characteristicity, so how closely 2 periods relate to each other, and transitivity is how they deal with chain drift. We also considered resource, so this is more of where the work Matt was talking about comes into things. Can the methods actually be dealt with in the environment that we're able to apply them into? Interpretability, so how well understood they are by our users, and flexibility, whether they can be used across different resources, different input sources, and different item levels as well. Stage 2 then was to assess the methods against some synthetic data, which we created different features on these synthetic data sets and assessed how each of the methods did. So this was things like obsolescence, high variability, high sales, dump price, features that you might expect to see in different behaviors of different items. And then stage 3 was to assess these behaviors of the different markets and items. So whether groceries or clothing's the data sets that coming in have any of these features, and whether they would still be applicable for our top ranked method. And if it wasn't, then we'd move down our shortlist until we find the highest ranked, most appropriate method. So you can see from the shortlist on the right-hand side that we've got the Gary Carmis with a fixed-based monthly expanding window as our top weighted method. And we also have the Gex Jevons in rank 4 with a movement splice is the top of the unweighted index method. But what you should be able to notice is that all of the top 10 methods here are multilateral methods as opposed to bilateral methods. So I'm going to talk to you briefly about what these multilateral methods are by comparison to our traditional bilateral approaches. So essentially, a bilateral index compares prices between 2 periods, or 2 months in this case. And we have 2 types. We have the fixed based and the chained. So I've got a little bit of an animation here that shows how that moves over time. So if you think of each of these circles as 4 months, as I click now, you'll see that the current month moves on 1 period. With the fixed based method, the first month always remains as the base month. With the chained method, we'll always have that change method as the previous month. By comparison, the multilateral index methods will make those comparisons across multiple months, so 3 or more time periods, all at the same time. So what this means in terms of product coverage is that if we were to think of this as a mock basket of goods that we might have collected from a website or from scanner data, and what we see quite often is that products come in and out of stock quite a lot. So they might be there 1 month, not the next. So where we have this increased product coverage, it means that we have a higher churn. And for our fixed-based bilateral method, coming to the April index, we would only be able to include product number 1 highlighted here, because it's the only product that is available in both January as the base month and April as the current month. Compare that then to the chain bilateral method, and we can only get 3 of the products included here, products 7, 8, and 9, because they're the only ones that are in March as the previous month and April as the current month. So we're missing quite a large proportion of our basket if we were to use a bilateral method. If we compare this with a multilateral method, we can use any product that appears twice within our chosen window length. So here, if we're using a 4-month window length, each of these products has appeared twice. It means we can let that product contribute to our basket and our overall index. So there were 2 main methods that were highlighted in our shortlist that I'm going to give a brief overview of as I can, because they are quite complex, but I'm going to do my best to simplify them as much as I can. So starting with our top ranked weighted method, the Gary-Khamis. So you can think of this as a quality adjusted unit value index, which is a lot of words, but I'm going to break each of those parts down for you. So the unit value of a set of homogeneous products can be calculated as the total value of sales divided by the sum of quantities. To make that a unit value index, we just measure the change between those unit values between periods. And then to quality adjust it, the idea is to just apply quality adjustment factors to the various item quantities to express them in the terms of a base item, and then we simply add those up. The Gary-Khamis index can be understood as an implicit price index, but in fact, it's just a value index that's being divided by a quantity index, is probably the most simple way of thinking of it. So to calculate the Gary-Khamis index, it's obtained by solving an iterative system of equations, which I've tried to summarize here on this slide. The overall index is included in both the equations here. So 1 and 2 both include our price index that we require. The transformation coefficients in box number 2 are implicitly defined by all the other price data that spans over the whole window of interest. And what we do is we iterate through these system of equations until the Gary-Khamis index value does not change between each cycle. So you keep iterating and iterating until you get no difference, or your threshold for difference is matched, and then you take that as your final index value for that period. And then the other method that I want to talk about is the GEX method. So GEX can be thought of as a family of methods, which is why we had it so many times in our shortlist. Whenever a GEX is calculated, it's paired with a bilateral index method. So we can have a GEX Fisher, GEX Tornquist, or a GEX Jevons are the most famous ones, or the most well-known methods implemented. But you could do a GEX Lespers or a GEX Pash, or whichever bilateral method you chose if you wanted. So the GEX is essentially a geometric mean of all ratios of bilateral indexes, where each period is taken in turn as the base. So hopefully this image sums it better up than the words. So we're trying to calculate the March index. So what we do is take the bilateral movements from January to January and January to March here, January and February, February and March, and so on and so forth for every month that you have in your window, changing down this middle column. And then you take the geometric mean of each of those rows. However, the keen of you amongst this might notice one problem. We're going to try and calculate March's index using April, but we haven't got April's data yet. And we haven't quite got a time machine yet at the ONS for us to go forward in time to see what the prices would be. So we have to think of a way to come around this. So we could publish what we have up till March, calculate it that way, and then when April comes along, revise all the back data. But under normal circumstances, we can't revise. So how do we come around this? And the answer is extension methods. So splicing is the most common method for multilateral methods to extend them over time. And I'm going to give you a quick example of the rolling window extension method. So if we look at this table, you can basically see what they're trying to summarize here, that you've got all the data is used from period 0, the first data point that you have, up until T, which is your current period of data. Then as you move on to your next month, you add that next month's worth of data in and you drop the oldest month, and so on and so forth. So you always end up with a fixed length for your window, but it's always got a variable starting point moving on by 1 month at a time. What does this look like in practice? So if you imagine this is the GEX index that's been calculated between January 19 and January 20, and then we move on to the next month, and we've calculated it from February till February of that year. So we've dropped the first month and we've added a new month of data on to keep the window length the same. And you can see that it would have revised all the data points in between February and January. So we don't want to revise everything. So what we're going to do is chain this on from January, moving it down like this to chain the two series together in the January 2020. And that's how you've calculated your February index. So this is the movement splice where the chain linking is done on the month previous to the one you're trying to calculate. But there's many different options for splicing. We could chain link on the first month in column. So this could be February 19. We could use a half window splice or a geometric mean splice, which would involve taking all the intermittent months and chain linking that way. The other option that we have for extending over time is the expanding window, which is more commonly used with the Gary-Khamis. So by comparison, you can see that this has a variable window length, but always a fixed starting point. So it includes as every month progresses, you're getting an extra month's worth of data and you just include that in. So you're not dropping anything unless you decide to update from time to time, which is what you can see has happened at time point T here. They've started again and dropped the back series. With the Gary-Khamis method, this is usually done once a year. I'm going to try and hopefully explain this with some pictures of the graphs now as well. So if you take the blue line there to be the movements between January and February, when you only have February's data, and then the orange line to be January, February, and March, when you've also included March's data, you can see that it would want you to revise for February. But what we actually do is to just join the new March point onto the previous series. And you do this all the way through the year as you get your additional information. And then if you were to start a new year, where you've calculated another year starting from 100 because you've rebased in January 2020, you then just chain that whole year back on. So hopefully that's given you a clearer picture of the multilateral methods that we're talking about using here. I'm going to quickly talk through some of our tests that we've run on this. So to assess the potential suitability of our shortlisted methods in the production of the consumer price index world, we produced a range of synthetic data sets which demonstrated isolated pricing behaviors to stress test each method's performance. So this was the base data set that we produced here. So we can see here and throughout the analysis that I'm going to show you that the difference between the weighted and the unweighted indices is greater on average than the difference observed between the weighted methods themselves. So this highlights that the presence of weighted information at the product level is arguably more important than the choice of the weighted index number method itself. Basically, the unweighted methods here are the dashed line, and the solid lines are the weighted methods. So the indices produced for the unweighted methods, so here we've got the Gex-Jevons with a range of different extension methods, and the fixed base and chain Jevons are all identical for this data set because all of the products are available in all time periods. So there's no churn, so they basically equal each other. So this is a product of a static market. So one of the important features was the high attrition rate, which we talked about earlier with regards to product coverage in the baskets. So it's quite prominent in web scraped and scanner data is that products enter and leave, driven by things like the fast fashion of clothing markets or rapidly advancing technology that you might see in PC, laptops, that type of thing. This feature highlights the reason that the multilateral methods outperformed their bilateral counterparts. So the graph shows that all of the methods fall in a similar way to what we observed in the base data, although the variation between the different index number methods is now a lot more. To assess the performance of each of the methods, we compared the sum of the absolute differences between the index values based on the simple base data and the index values produced using the data set with high churn. So for our data set, when the churn is high, the fixed base Jevons and the chain Jevons vary further from their base indices than the multilateral methods, which is great. That's what we'd expect. As we already noted earlier, the fixed-based method will use an ever-decreasing proportion of the available data each month of the year, so it becomes less and less representative of the item. And the chain bilateral methods will typically suffer from chain drift, so over time we'd expect them to become increasingly different from the baseline data set. So given the properties of the methods, we would therefore expect the sum of absolute differences to increase for the bilateral, fixed base and chained methods compared to the multilateral methods over time. We also looked at product obsolescence. So obsolescence occurs when a product ceases to be functionally competitive with other products. So this may occur when a retailer stops producing or marketing a product because the product becomes undesirable to the consumer. This is usually related with like high-tech products such as smartphones, because when a new model is released, the older models become unfashionable and are often withdrawn from the market. The problem of using a fixed base bilateral method is highlighting here because at period 13, which we can see here, this green, there are no longer any matching products in the set of the current and the base periods. Therefore, we can no longer create index values and the time series ends. We can also see from this that the unweighted methods result in indices significantly lower than the weighted methods in this scenario. This isn't surprising because they don't use the expenditure information that we have available. Instead, they give each product in the basket equal importance. The weighted methods will identify that in this obsolescent data set, products with increased popularity do not reduce in price as quickly as products that leave the market. Again, showing that there's that importance to have the sales information at all, more so than which method we choose. And just to show you an example of us using it on real world data. So this was some soft drinks data that we got our hands on, but we also tried beer, toothpaste, shampoo, and got similar results, but just wanted to show one of them here. So whilst our stress testing of the methods isolated features to understand how index number methods would respond. We're aware that in the real world, these features will happen simultaneously. So the two main observations that we made from the 5 items that we looked at here in our case studies is first, the differences between each method's indices and the extension methods are way more substantial in practice than we observed when we were stress testing the methods. This is likely impacted by a longer period of data than what we used in our stress testing as well as seeing the features occurring simultaneously rather than in isolation. So we can see that the different extension methods cause the indices to differ significantly in the later parts of the time series, a result that is being replicated by many other national statistical institutes recently. And secondly, we can see that there's an upward bias from the GEX-J methods in comparison to the weighted methods, which is likely because consumers substitute towards products that are on sale, and this is not accounted for when we use the unweighted methods. So again, highlighting that having information on sales values or even approximates of is arguably more important in this context than the choice of the index method itself. So where are we going with this in the next few steps for us? So we're going to continue to review international literature and update our framework. So this will see us reviewing the criteria that we use based on other people's studies and research, and updating that shortlist if it needs to be done. We're also going to be extending our research into extension methods and the impact of the choice of window length. So how that window length, whether we choose a year, 2 years, 3 years, impacts the accuracy of the method and which extension methods react the best. And we're going to do some increased testing on real world data. So as we're getting more and more data into the ONS to be able to look at and do our research on, we're going to expand that way as well. So a few take-home messages from the research work that we've carried out on this to date. The multilateral methods offer increased product coverage, the ability to weight at the product level, and makes better use of the product information that we gather from these dynamic alternative data sets. So the multilateral indices are better than the bilateral indices. Our testing has shown that the Gary-Karmis, the Gex Tornquist, and the Gex-Fisher adequately represent each of the features tested, and they rarely diverge by more than a single percentage point in our feature analysis. The difference between our weighted and unweighted methods was more significant, which highlights the importance of us using approximates of or the actual sales values at the product level, and that this research is arguably more valuable than the choice between the method and extension method themselves. And lastly, that we did see greater differences between the extension methods when used on a longer period of data using our real world data. So this is something else that we're going to continue to investigate. I think that's it from me. So if you have any other questions, I'm happy to answer those. If not, I shall hand you back over to Helen. I think Helen's wrapping up.
I don't really have a lot to wrap up, actually. Just thank everyone for coming. Unless there's any further questions.
Thanks. There was no further questions on Slido, but thanks, Alex, for explaining those quite complex methods in such a clear way. But yeah, we'll be on the line for a bit longer, so do carry on with your questions if you have any. And I'll pass back to Nikki to close up as well.
Thank you. Just a second. Yeah, just want to say thank you to everyone that has joined into today's webinar, and thank you to all the presenters for today's work. It was a great session. I just want to let you know that A recording of today's webinar is gonna be hosted in the Best Practice and Impact YouTube channel. And also you can find all the presentation material from today's webinar on GSS website, and also information about any upcoming webinars. You can also join us on Slack. There's GSS Center Webinar Slack channel. And if you have any questions about today or any future Center webinars, or also if you would like to contribute and share any idea about any future webinar, please contact us on GSS Help Statistics Gov UK. So thank you everyone for today, and have a nice day.